So what we were doing is this. Okay, a quick recap that we are trying to obtain the velocity profile for this particular problem where this bottom plate is moving with some constant velocity here for all t greater than equal to 0. So this is a boundary condition. Okay, and initially this fluid is rest, so velocity 0 everywhere. It's a unidirectional flow with gradient across the flow direction. Okay, and we are assuming that the top surface is very far from the bottom surface. When we say very far, that is always with respect to time. So this height h, if I say this height is h, this h can be treated as infinity only if you remember, only if the time scale over which you are analyzing the system is very, very less than h squared by nu. That's what we learned in the last class. Okay, and this time regime we can say early time regime. So we are going to solve this for early time regime, and of course for in future we'll also solve it for t of the order of h square by nu, so that momentum will reach to the top this top open layer, or it is confined in, it may be confined between two walls also. Okay, right. And this we have guessed the velocity profile should look like this. Okay, and then what more we guess is as follows. Our guess was, in fact our main goal was that can it be uniquely expressed by a single master equation, all these variables. We have Vx as a function of y and t, right? So what we want is that combining all these variables and get a single curve or a single master equation. So what we proposed that probably if we do this Vx by V naught and y by delta, okay, y by delta, then probably we can have such kind of master curve. Okay, and this we have said as eta. Okay, so eta is the similarity variable because all the curves are similar. So if we do such kind of transformation where delta we said is square root nu t, so eta is nothing but variable combining the space and the time. We are expecting this all curve will lie on top of each other and we should get a master curve. That is our guess. Okay, so that's what we are going to see today, whether we are indeed getting this or not. So if you see our governing equation for this problem is dou Vx by dou t, kinematic viscosity, dou square Vx by dou y square. Okay, all other assumptions are there, and of course it's Newtonian, homogeneous, fully developed, all those things are there. Now what is important here is that whether we know the analytical solution or not. What does it mean by analytical solution? Where you can express Vx in functional form, okay, as a function of y and t. You can certainly solve all such types of equations numerically. And that's what we do in real life. Either it's a rocket science or petroleum science. In these days, this is the era of numerical solution. Okay, we solve everything numerically. And it is not confined to only chemical engineering. All engineering branches, even in you name it, you can use this numerical technique. So it is very important for you to equip with this solving by numerical technique. So that's what you are going to do in the assignment. Okay. So I'll share the slide how you are going to write. I'll share the algorithm. Right now also I'm going to show you how you will do it. And then you are going to solve all the problems which you are going to do in this module numerically. And that will be asked in exam also. I am not going to check it, Only first assignment you submit numerically, so that at least you will practice. Rest of the problem, don't forget to solve it numerically. Okay. So that in exam, if I ask, this is the write down the Gurney equation, solve it numerically, get this curve, you should be able to get it. You are free to use any language, MATLAB, Python, whatever you want to use. You are free to use the libraries to solve PD. If you go to these packages, there are libraries who can directly solve these PDs. So you don't need to discretize it. It will do it by your own, by its own. But that I leave on you. I am going to tell you the, the main recipe where how this PD get solved. You can use that algorithm which I am sharing with you. I'll also upload the slide, or you can directly use the library. Okay. And then we will go to analytical solution. Okay, let's mark the attendance just. Sometimes we should do that. So marking is very simple here. And I'll award 1 mark to everyone, at least 0.5 marks. So let me download the, let's see from where I can do this. Achha, so I'll leave the meeting for a minute so that I can download the attendance list, and then I'll again join. So just wait for me. Huh? Okay, so I think I have to share my screen again. And recording is on, I guess. Achha, someone is already recording, so that's great. And yeah. Right, so let me show you that how we are going to solve it numerically. And if in case any confusion, you can stop me. Okay. So I am showing you for a, a general case, and then you can implement it here because that's how I have written it. So let's say if your equation is T is any variable, okay. K is your diffusivity. It may be thermal diffusivity, momentum diffusivity, mass diffusivity, whatever it is. So if this is the equation, if you want to solve it numerically, okay. In our case, it is y, so you make it y, right? Let's make it y so that you will not get confused. So let's say T is function of, or let's make it V if you want, so that you will not get confused. So we have this new here, momentum diffusivity, and we have this Vx, and Vx is function of y and t, and we are going to solve it numerically. That is our. So for numerical solution, you don't need any, any kind of excess transformation or similarity variable. Numerically, you can just solve. You just solve it. That's all. You don't need this similarity transformation and finding this variable eta. Nothing. That's the beauty of numerical method. Okay. So I thought before going to analytical solution, I should cover this. So what we are going to do? See, there are various methods. If you go to explicit method, then what you are simply going to do, see, remember, you are going to discretize your, let's say, what you are going, so you have one grid is for y and another grid is for t. You know, you will solve for different y and different t. So what you are going to do, let's say you have this y0, y1, y2, y3, and so on. Means you divide your domain, this y domain, in different grids, and then you have different time steps. So what you are going to do, first write this derivative, time derivative using finite difference. So what you can write is at Vx, okay, at any, let's say, so rather than Vx, I'll just write V, so that I can write the subscript. So this will be simply Vi at t plus 1, or rather than t, let's say kth interval, so k plus 1 minus Vi at k. So you are writing this derivative at ith node. You see, these are, so I is nothing but 0, 1, 2, 3, and so on. This is your y, right? And you have discretized the y in, let's say, n or m, whatever you want. Let's say this is your y0, that bottom boundary, y1, y2, y3, y4, y5, and so on. And this is your delta y. So of course you have kept delta y same. So y2 minus y1 is delta y, y3 minus y1 is delta y, and so on. So this is your step size in space domain, okay? And your step size in time domain is delta t, okay? This is nothing but ti plus 1, or sorry, for time we have used k, so use k, so it's nothing but t of k plus 1 minus t of k. It's not power, it's superscript, okay? So what we will write it, this divided by, this will be simply my time step, delta t, okay? This is equal to, now this is new. What you are going to write this? There are various ways to write it. One way which we use in explicit method is simply, so this is our new kinematic viscosity, and then here let's change the color, and I'll share this slide with you, like the typed slide. I have given it to TA. He is typing it, so that's not a problem. You can focus it here. So what you are going to write it as V I plus 1 at kth time minus 2 V I kth time plus V I minus 1 at kth time divided by delta y square. So I have written this double derivative using central difference formula, which you can get back to your numerical method book or any notes where you will find this. I have written this derivative using all the variables at kth time. Okay, you see everywhere where this subscript is k. One can say, why you are writing this k? Use k plus 1th derivative. Yes, that also you can do. But then that method will be implicit. Or one can say, why kth plus? Take the derivative at this value at kth derivative and k plus 1th derivative and take the average. So depending on this right hand side can change. All these three methods I'll share with you. The last one, where you use the average of kth time node and k plus 1th time node to write an average of that. So this derivative is the average of derivatives at 2 times, kth and kth plus 1. That is called Crank-Nicolson. Okay. Implicit methods are surely converging. Okay. Another thing which you should take care, which you will find in that slide also, that okay, let's at least let's do the implicit method, explicit method. Implicit method you can follow in my slides, because that is easily doable, and you can refer books also. So what will happen when you will discretize this? Okay, and when you will arrange it, what you will get? Let's see, just to get a feel. Let's use this one. So what we'll get is V I at k plus 1. This is explicit method, because only left hand side will be unknown, right hand side everything is known. In implicit method, in each equation, there are two unknowns or three unknowns, and then you prepare a tridiagonal matrix and then you solve it. All equations together, simultaneous equation. In explicit method, you will keep on getting the next value. Just see. It is easier, but it is less like you have to take care of the convergence and all these things. Okay, anyway. So this, if you'll arrange it, you can write it Vi K, and then plus K delta T by twice by delta X square. Okay, and then here you have V of I plus 1 K minus twice V of I K plus V of I minus 1 K. And this quantity many times known as lambda, and this lambda for convergence in case of explicit method must be less than half or preferred 1/4.
So is it K or is it mu?
Oh, sorry. In case this is mu, yeah, that's fine. You are smart. I mean, this many things you can correct. You are right.
And also, sir, it will be del y square, right?
Yeah, yes, of course, right. These things you can do. So, fine, good. At least someone is. Thank you. Yeah, right. So I just copying in terms of X. So yeah, right. So this is clear. So what you see here, and it was Anik, right, who was answering?
Yes, sir.
Yeah, Anik. So what is why we say explicit? I'm sure you got it. If not, then I'll help. So what you see here?
I don't know, sir.
So my question, okay, maybe I didn't explain properly. So what I want
Sir,
to ask,
sir,
yeah,
it is called explicit. So it is called explicit because we are not for finding the next variable, we are using the known
right.
quantities.
That's all. Yeah, wonderful. So that's all. So for knowing the values at k plus next time step, you are using all the values in the previous time step. So you are not solving all the equations together, like you are going one by one. Okay. So for example, you see at t equal to 0, you know this value at all points. What is the value of VIs at t equal to 0? Whoever was answering last time, yes, what's your good name?
Sir, Cyan.
Cyan. Yeah. Cyan se main baat nahi kiya bola. Yes, Cyan. So yeah, so this, what is the value of Vi at t equal to 0? Like the first time step.
Plate velocity, no slip.
No. So don't get confused with boundary condition, initial condition. That's why every time I am emphasizing this. I am saying when I say the whole domain means you are considering all y's, isn't it?
Yes, sir. So 0, sir.
0. So for k equal to 0, or let's say for first time step, for all domain, all these vi's are 0. So for, let's say, if you say first time step k equal to 1, all vi is 0. Okay. Right. So that's it. And yeah, so let's see if you, so this is the explicit method. So let's say if we solve this equation, if you want to, in fact you should try, because I don't have the values. Okay. So you take the value of this water whisk. This is new, not mu. Right, and yeah, not me. Yeah. So you take your time step, you have to just take care of this, that this you are satisfying. Okay. And then go ahead. That's all. Let's see what you get. Okay. So anything else? Acha, let's see whether this implicit method will work on this or not. I'm just wondering if velocity is 0 everywhere. Otherwise, we have to probably go for a implicit method. Let's see whether it will work or not. So if we say the first time step, everything is 0. So it will not go anywhere, isn't it? Is it going anywhere? Just check. So this is V of I plus 1th. These all are at k time step. It's becoming 0, isn't it? Sayan, if you go with this explicit method, will it work? I'm just wondering, it will not work.
Yeah, I think it is becoming 0.
Yeah, it's not going to work actually. Okay. Okay, if we write it for k plus 2th, yeah, it will not work. We cannot go with this method, I think. We cannot proceed. That's my guess. Because if I have copied all the variables correctly or not. Anyway, slides will be with you, so you can try by your own. Let me see that.
Hello, sir.
Yeah.
I'm not getting why this method will not work.
No, because say, let's say you start from, you want to know the values at k plus 1th time. Okay.
Yes.
So let's say we k equal to 1. So we want to know k equal to 2. So velocity at second time step. Okay.
Sir,
So,
but for I equal to, let's say 1, V1 0 will be, V00 will be V naught. So it will not be 0.
there is boundary condition also. Right. Yes.
Boundary condition is there.
Yeah. Sorry. Yes. Correct. Yeah. So let's write it then. Yeah. It's better we write it here. V of I plus. So we are, let's say, writing it for I equals to. So I is my time domain, space domain, and k is my time domain. So this is for y, this is for t. I agree with you. Let's write it so that everything will be clear. So what we have is v at second time step. Let's say v2. Sorry, this is space. So we want to know v I. Let's say I is 2, or I. Let's say we start from, look this way. Everything is from 1. Let's say 1, 1, 2, 2, 3, 3, 4, 4, and so on. So this 1, I equals to 1 corresponds to boundary, bottom boundary. So the boundary condition associated with y equals to 0. Okay, where our all vi's are v naught, as someone said. Thank you. That's why we should write. If we start guessing just to see the equation, we will all get confused. Okay, so what we are saying, let's say we want to know the values. So if I write this way, that v2 at, let's say, time step is also 2, v2 is equal to v of 2, 1, okay, plus whatever that lambda mu delta t by delta x square, okay, this multiplied by what we have is inside v, and then this is I plus 1th variable. So this will be again, so we are putting I, 1 is known, 2. So this is for I equals to 2, because I equals to 1 is known. So this is coming a v of 3, okay, 2 plus 1, 3 at 1, okay, minus twice of v at 2 at 1, and then plus v of 1, I minus 1 is 1, 3, 2, 1, just let me check, 3, 2, 1. No, I plus 1, so it is 3, then I is 2, fine, and then this is 1, perfect. And then this is at first time step. So right hand side is at the first time step, k is 1, right? So let's find out v22 what we are getting. So what is the value of v21? Is 0, isn't it? Just check I am right or not. Let me first write it here. So what we should write at v1 for all t, that is whatever k, this value will be always v naught. Now if I am wrong, just interrupt me. So what I think, so v21, v2 at, okay, we have to write this condition also, no? So this we have written boundary condition. Let's write initial condition also. Initial condition. Initial condition is what? That V initial condition means for whole domain. So for any I at first time step is 0. Okay, so this we are going to use when we are going to start this calculation. So if I am wrong, just correct me. So let's say, although this you can do by your own, but I thought at least one example I should show you. So V2, 1. So where we should go? So this is 0. If I am wrong, just correct me. Plus this lambda variable, okay? And then V3, 1. This is also 0. Because see, if time subscript is 1, everything is 0. Minus 2 V2, 1. We have to come here, right? No. V2, 1. V2, 1 is also 0. That is fine. Plus, yeah, this one will be, anyone? V1, 1 will be? Yes. Who was saying that? Yeah.
U0.
U0, right?
U0.
Right, perfect. So V2, 2 is lambda U0, okay? In fact, rather than saying this 2, since you can solve it for whole domain, I think same value you should get, isn't it? If you do it for, no. You have to do it now for the whole. So once you know V2, 2, then we have to go to anyone? Next will be what? First, you have to complete this whole. So how you are going to run on the grid? Let me tell you. First, what you should remember when you are using explicit method. First, let's say T1 step, all the values are known. Go to all the grids, run on the Y grid and get the value of those variables on all Y for T2. So basically what you need to know is V for all I, or let's say, so what I should write it, that V for second time step, okay, for all I's, for all I's. So V2, so what we have calculated here, V2, 1. What is the value of V2, 1 again? Anyone? Remember this subscript is for, so what is V2, 1? U0, you see here, V2, 1 for when, am I right or not? Wait, yeah. So this, whenever you have this subscript 1, the bottom one, it is boundary. So it is always U0. So V2, 1 is U0. Then what we calculated, V2, 2, you see, lambda U0. Okay. Then you will calculate V3, 2, because first complete this time grid. V4, 2, V5, 2. Okay. Once this is completed, then you know all the values, all the values at second time step. Then go for third time step and so on. So this algorithm you have to write. Okay. For example, if you want to calculate, let's say using the same equation here, this equation, V3, what you will do? Let's say you want to know now V3 at second time step. What is our target? You see, V1, 2 is known. V2, 2 we just calculated. Now V3, 2, V4, 2 and so on. So let's say if you are interested in V3, 2. This we have calculated lambda U0. Now V3, 2. So for V3, 2 again, let's write it. This is the last calculation which I am writing, and then you can go ahead. So V3, 2 will be V3, 2 will be, so this I we are taking as 3, right? So V3, 2 will be V3, 1 plus lambda times V4, 1 minus twice V3, 1 plus V I minus 1, that is 2 V1. Okay, let's calculate it. What we'll get? So what is this V3, 1? If time is 0, this is 0. Lambda, this is again 0. Wherever time script is 1, that is 0. This is 0. And what is V2, 1? Again, What is
Zero.
V2? No, you know, right?
U naught.
Have I made any mistake? Just check. Wait.
No, sir, it will be zero because V2 are there.
No. Then there is some. Then let's check it. Where we are making. So V31. Oh, V31 is. Wait. Let me see. I have V32. I want to know, right? So this is fine. This is V31, which is fine. Lambda times 3 plus 1 4 V41 minus twice I is 3. So V31. This is fine. Plus 3 minus 1 2. That is V2. Yeah, okay, 0. Fine. So okay. Just check whether it is correct or not. Are we getting V30? Fine. So let it be
Yes, sir.
0. Because you can guess it also. And again, V4, V5, all other things will be 0. It's simply telling you the numerical solution also that only one value you are getting positive and others 0. That's how it should be. Because momentum has penetrated only up to one grade. Then after some time, second grade, third grade, fourth grade, so and so on. So numerical solution is also telling you the same. Okay. That up to for whatever time step you have chosen, and so see here you that's why numerical solution while doing the numerical solution you have to be very careful while taking the time step. So let me discuss that thing with you. If you understood this, remember this is explicit. You
Sir,
better yes.
so I have a doubt. Like, said that you said the initial condition is Vi1 equal to 0, right?
Right. Yeah.
So
Yes.
when we are calculating V22,
Yeah.
then you are saying that V11 is U naught, sir. But it
So
should be
let,
0,
let's
right?
see what I said. Yeah. Which one? Here.
No, sir. While calculating V22.
V22. Okay. Let's see where we have here. Tell me. Hmm.
Yes, sir. Yes,
Which one?
it is that at the last term it is V11, right?
V11. Yes.
Yes, so according to the initial condition,
No.
Vi1 should be
So
equal to
that
0.
good. Any other anyone who has this doubt, listen carefully, and that you will always get confused if you let take care. See, boundary is different. Initial condition is for the whole domain except boundary. Okay. So boundary condition,
Okay, sir.
okay, is so when you say this, initial condition. I think your doubt is clear, but still let me make it clear for the whole class. This initial condition is true for whole domain except what?
Boundary.
That's why we have special bound. So that's the thing. That's what you should always remember. Boundary condition you cannot account both together. Boundary is boundary. Okay. So let me write in terms of variable. If you are again getting confused, is let's see our problem. Let's write both conditions so that there will not be any confusion. So this is our plate, which we are pulling with some velocity. So what is our initial condition? Our initial condition is that Vx is 0 for all y. When? When you say initial condition, when? At t equals to 0. Initial condition means t equals to 0. So now one can ask, sir, you are saying for whole y. But then when you say for whole y, boundary is excluded. You have to remember this. Boundary is excluded in this whole y. Otherwise, if you boundary condition is something which drives your problem. Okay, so boundary is excluded always. That's why you have separate boundary condition. Boundary is excluded. So let's write out boundary condition then. At y equals to 0, my velocity is v naught for all t. Doesn't matter what time it is. The process moment phenomena has started. Sorry, for all t, not y. The moment phenomena has started, the boundary will always maintain this velocity v naught. Always. So we cannot mix it up. Is it clear? Like, does it make sense?
Yes, sir, I got it.
That's why whenever you have this lower subscript 1, it doesn't matter what is the top subscript. It is always going to be u naught. Clear? So V1K is always u naught. Okay. Fine. And you will get more feel when you will write this algorithm using pen and paper. So So do it for all three methods. I'll share the slide so that will get a help, because no one can remember how we write this. Okay. So the explicit method which I discussed, simple implicit method, and Crank-Nicolson. The Crank-Nicolson is the most preferred method. Once you prepare the code, it will help you in exam, anywhere where you have to solve this PD or similar kind of PD. So do this effort. I mean, it will take probably one day to get comfortable with any coding language. Okay, but do it. It's this effort you must put. It doesn't matter in which profession, it will always be a set for you, this programming skill. And MATLAB is very easy, because at least for my case, no one taught me MATLAB ever. You can, because anyone can learn MATLAB by its own, or Python. Whatever you are coming in your mind, just type it on the Google, use that command, see what result you are getting. And that's how you can learn. So I don't remember any command in MATLAB. I always Google it, paste it. That's how you should do. Okay. So there is nothing to get worried. Few of you are thinking that, okay, this, how we are going to do this programming. We have not done it, up to that extent so that we can write our own code. You can do it. Just start trying. Okay. If you'll ask me, I'll extend the date for submission. That is fine, by 1 week. But everyone should do by his or her own. Don't copy from somewhere, or don't ask. You can ask help from your friends, but write by your own, because you have to write it in the exam. Okay, not the code. I mean, I'll ask the algorithm on your by pen and paper in your that answer script, and then the results which you are getting from code of that. I will never ask that submit the code. Submit the code means submit the algorithm, but still you should practice. Okay, right. So if this is clear, please try it with first the implicit method, and then explicit method, and then implicit methods, right? Okay. So let me conclude it so that you will not get confused. That
Sir, then are we going to update our boundary condition by every iteration?
no, not at all. Boundary condition will always be same. Do you want me to solve at least for one time domain?
So if we do this, then if we increase the value of k,
Yes.
will it be 0 again, or?
Okay, let's write it. Huh? Otherwise, you will keep on getting confused. Right, wait. Let me write the equation again on the fresh page, because it's important and you should learn. So first let me write it, and then you tell your doubt. There is no confusion at all. So I am writing it here. Huh? V of I k plus 1 is equal to, and then you can ask your, what is your confusion? V I k plus lambda times, lambda is nothing but k delta t by twice k mu. So lambda is nothing but mu delta t by delta x square, where delta y square, where delta y and delta t your time step and this space step. Okay, lambda times v of I plus 1 kth minus twice v of I kth plus 2 of vi minus 1 kth. Now you ask your doubt. I'll answer your doubt. For which time step you are saying? I'll tell you. Tell me. Or which?
So for V22 we found it like lambda u naught. So
V22, right? V22. Let me write it. Huh? So V22 is lambda v naught, right? And other this V32, V42, what we are getting 0, right? Now you say, tell me.
Sir,
So now, wait. Sorry. Now we know the values at t equal to second time step. Is it? T equal to 1 is already known, because that is initial condition, except boundary, right?
Yes,
now,
sir.
Yeah.
Sir, my doubt is for t equals to 3, will it all be 0? Because V2.
Let's see. Okay, t equal to 3. Let's write it. So you help me. So V, let's say, so do we need to write it? What's her name?
Sir, Cyan.
Cyan. So V1, and then let's say 3. Do we need to write it? What is the value? Tell me first, and then we'll move. For everyone who are not.
So this should be, I guess, 0. So.
No, why? It is boundary. That's
yeah, it is boundary. Yes.
1 is always boundary. So
yes.
It's always going to be u naught. It doesn't matter what is the super subscript is, the time subscript. Boundary is boundary. That you have to always, either you solve analytically or numerically. If you get confused with boundary and initial condition, you are going to, it will lead to more and more confusion.
Okay, sir. Then I got the doubt. I mean,
Uh,
I
cannot be-
ignored this boundary condition.
Yeah, boundary is fixed. So that's why I'm saying V1 for all K, it's always U naught. There is no doubt about it. This is our boundary condition, numerical in terms of, numerics, like discretized way. Or if you write it analytical way, what we say, V at Y equal to 0 is always U naught for all T. Right? Both are same. Clear, Sam?
Yes, sir.
Okay, let's move ahead. So do it. I will increase the submission date, let's say by 4-5 more days. Right now it's 31st January, but try your best. I want everyone to write your first Python or MATLAB code. For many of you, not everyone, or many of you are already habituated of this. Maybe you have written many codes, but those you have not, this is the course. This is a chance where you can learn this, and then you can implement it anywhere. Right. And anyway, you'll be needing this code in exam. I will not refrain myself for asking you that, run this or what answer you are getting and so on using numerical solution. So now we will come back. So this, why I have taken so much time on this numerical solution, because every time whenever we will have new problem, we'll find governing questions are almost same, only the boundary conditions are changing. I'll write the governing question, the boundary condition. I'll explain you the phenomena. I'll ask you to solve numerically. My work is done. Okay, I'll give you the analytical solution, and then you will try to see what is the match. The analytical solution is the correct solution, the precise solution, and numerical one is always approximate. So you'll see depending on your time step and grid step, how close you are to the analytical solution. More closer you are, better is that your numerical technique is, or whatever values you have taken. Okay, that is point number one. Second point, which is more important, and that's why I thought the whole class I'll spend today on how we solve equations numerically. I am sure you have done it before, but probably have not implemented up to a greater extent. So here you can. Another important thing. So while choosing this time step, so I already told you that delta t and delta y you should choose in such a way that this number lambda, which is nothing but nu delta t by delta y square, should be less than half, preferably less than 1/4. Apart from that, another thing which you have to take care is as follows. See, there is a time scale associated with the phenomena. So the time scale, let's say capital T, after which the disturbance will reach to the top, we know that x square by nu. And let's say this value is coming 5 seconds. So you have to make sure delta t should be sufficient enough with respect to this t, so that you can solve it for early times also and larger time also. So if it is 5 seconds, let's take delta t 0.01 second. And after that, and whatever delta y you want to take, or delta you can decide, you know delta t, you are going to take 0.01 second, accordingly you take delta y, so that if this lambda remains less than half and you get the convergence for explicit method. Okay, so just check this time. If you are using water, what is the time scale after which this momentum will roughly reach to the top one? Okay. Great. So let's start the analytical solution quickly, and then we'll complete it in the next class. And now from now onwards, we'll be increase our pace, because now everything is clear to you. Now, since this is transport phenomena and all the phenomena is analogous to each other, whether it's heat transfer, it mass transfer, it momentum transfer. So now I don't need to repeat this thing again and again. So that's why I spent 3 classes on, making the strong background. The foundation should be strong. And second thing is that numerical solution are more applicable. In any engineering problem, you can implement it. So you must learn it. That's why I thought first go for the numerical solution. You remember the beauty of numerical solution, you don't need to take care of early time regime or larger time regime, smaller y, larger y. You are solving it for whole domain, and you will get your answer. And then I'll show you for which domain analytical solution, for For different time regime, we will get different analytical solution. Okay, so let's now solve it analytically. Up to this point, anyone has any confusion? While I am writing this Kern equation, please ask. And somebody mentioned in the last class that you have already explored such solution, which is called error function for early times. Anyway, that will eventually come. So let's see. So what we are claiming, f, a function which is vx by v naught, is function of a variable which is y by delta, and y by delta we are saying eta. Okay, right. So our eta is y by delta, remember. Now what we will do, let's take this left hand side, dou vx by dou t, and do this. I can always write vx as f into v naught from here, you see, by dou t. But my target is that I want to transform everything from this yt domain to f eta domain. So what I am going to do, and with this derivative, is dou eta by dou t. Okay, this is equal to v naught dou f by dou eta. What is dou eta by dou t? Partial derivative eta with respect to. So in this eta, which one is function of time? Anyone? In this eta, which consists of, which is made of y and delta, which one is function of time?
Delta.
Delta, very good, because it is growing with time. So let's find out the partial derivative. This partial derivative, dou eta by dou t. Dou eta by dou t will be, anyone? Y will be treated as a constant. It's a partial derivative. This will be minus 1 by delta square and dou delta by dou t, which is nothing but y minus delta square delta dash. Okay. And what is y by delta, by the way? Anyone? What is y by delta?
Eta.
Eta, right? So this is nothing but minus eta delta dash by delta. Okay. So that's what we are going to write here. This term is nothing but minus eta delta dash by delta. Delta is function of time. Okay. So this is left hand side. Let's see the right hand side. And then we'll equate it and then you can leave. So right hand side is right hand side is a double derivative. So first gets this first derivative, partial derivative, dou vx by dou y. Again you can write it f dou v naught by dou y, but you want to transform it into eta, so you write it this way, dou eta by dou y. Eta is nothing but, you are already knowing, eta is y by delta. So what is dou eta by dou y? Anyone quickly? Cyan, what is dou eta by dou y? Partial derivative. It is function of time only, delta. Yes. Bhavna, what is dou eta by dou y?
1 by delta t.
That's all. Yeah, 1 by delta. Because see, it's a function of time. So, whereas you are differentiating with respect to y, so this 1 by delta is constant. Differentiation of y is 1. Okay. So 1 by delta. Of course, delta of t is hidden here. I will just write delta. Right. So this is first derivative, but we are interested in second derivative. So how we are going to write it? Like write this way. We want dou vx by dou y, dou of y. we can write it dou of Vx dou y dou eta by dou y. Okay. And what is the value of this derivative? We already got it here. Okay. And you are going to differentiate it with respect to eta. So what we'll get? So this is fine, dou Vx by dou eta. Sorry, dou eta by dou y is 1 by delta. So let's don't get confused. Let's write it properly. This is equal to what? V naught dou f by dou eta by delta. Up to this point, everything is fine. Yeah, perfect. Right. So now for double derivative, I can write this. In fact, let's do one thing. Let's differentiate it here itself. So that we have 2 more minutes, so we can complete this derivative. And from next class, in next class, we can complete this solution. So next class, we'll do one more problem. So now differentiate both sides with respect to y. So dou Vx of dou y, dou of dou y is equal to V naught delta dou f by dou eta. Okay. Dou of dou y. But we want it with respect to eta. So this is fine. This you can keep at least here. I can always write this as dou eta by dou y. If you have any confusion in any step, you can stop me. Right. So what it will be, anyone? What will come out of this derivative? Rakshit?
Sir?
So is it clear up to this step, what I have
Yes.
done?
Yes, sir.
I am differentiating both sides with respect to y. But
Yes.
then I want to take it to eta. So dou eta by dou y. So what will be this thing? Just tell me. Which one will come out of this derivative? Which variable?
V naught by delta.
V naught by delta, because delta is function of time. Okay.
Yes.
Whereas eta is a function of both. So you have to take delta out. There is no, because it's a partial derivative with respect to eta. So what we will left with, Rakshit? If you know-
Dou by dou eta of.
Right. So second derivative, right?
Yes.
That's it. And what is this term? Dou eta by dou y, 1 by delta. We already know, isn't
1
it?
by delta.
So eventually it will come out V naught by delta square dou square f by dou eta square. Okay. So see what we have done up to this point. The left hand side and the right hand side. This is our right hand side. Nothing but dou square Vx by dou y square. And the left hand side we got here this number. So let's put it together. So if you'll put it together, the left hand side is what? Let's see what is left hand side. V naught dou f by dou eta. V naught dou f by dou eta minus eta delta dash by delta minus eta delta dash by delta. This is equal to, what is the right hand side? Right hand side is V naught dou square f by dou eta square 1 by delta square. Okay. Yeah. Now let's cancel whatever is getting cancelled. And there is a new also, by the way, don't forget it. This kinematic viscosity, momentum diffusivity. So V naught get cancelled. Let's cancel it. 1 delta get cancelled. Okay. And then we are going to write it this way. Dou square is, if I am wrong, you can correct me. Dou eta square divided by eta dou f by dou eta is equal to, I think, minus delta dash by delta into nu. And from here onward, we can use, the concept that, see, what is this is function of what, anyone? So I have just, up to this point, I have just rearranged it, nothing. I have taken the whole problem in eta and f domain, and then I got this eventually. So this is only function of what? Anyone? Bhavna? Is this function of time? So this is only function of time. Okay, time domain. And this is function of both time and space. And I am saying both quantities are equal when it is possible. So this thing is varying with both with respect to space and time. And right hand side is not varying with space. It is only function of time. When these two things can be constant. Sorry, when these two things can be equal. Anyone? Any guess?
Space is constant.
Value is constant itself. That is the only case. You see what we are saying, g of y and t is h of t. It is only possible if both values are constant. Otherwise, there is no possibility. If it will be a functional form of both y and t or only t, it's not going to work. Okay. Acha, constant of what, by the way? Constant of what? So if I am saying g of y and t equal to h of t, when it is possible? Constant with respect to both y and t or with respect to only y? Manish?
With respect to y.
Y only. So it can be a function of t. So remember, it's a constant, but constant with respect to y. So now we will see where it lead to. Okay. Right. So that's all. Next class we will see that how we'll find this value of c. Okay. Thank you. You can join the next class, and the solution is given there also, so you can have a look on into that what solution we'll get. Okay. Thanks.
Thank you, sir.
Thank you.
Thank you, sir.
You have another class now after this, or anyway, I will not stress this class. I'm just asking. Do you have another class after this class? Sayan?